Welcome to Maths with EJD, and I've been talking about integration in the past few videos. Today, I'm going to talk about integration of compound fractions. That may not sound too familiar, but of course, you know about partial fractions. So when you sum fractions together, you end up getting a compound fraction. And in the same vein, compound fractions can be resolved into partial fractions. So there are times when we have to integrate compound fractions, right? In such cases, we have to resolve the compound fractions into partial fractions for easy integration. So some compound fractions are hard to integrate. So it may require you to resolve them into partial fractions. You know, we've dealt with things that look like that, like rational functions previously. Like we saw a case where you could divide by whatever is at the bottom. Like you have all the expressions at the top, and you have only x or x squared down there, or even x cubed, or maybe just one term. In that case, it's still easy to divide each term at the top through, and you get your result. Something like if you have say you have f of x equals like x cubed plus x raised to power 4 minus 7 all over x squared. You know, here you can still divide through and you get x plus x squared minus 7x raised to power minus 2, right? So this is still, so in this case, you can divide. Then we've also seen the case of derivative function ratio, where what you have at the top, say you have at the top, you have, okay, let me even start with the bottom. Say you have 3x squared plus 7x minus 1 here. And at the top, you have 6x plus 7. In this case, if you if you differentiate this, you get this. So in that case, we already know that to integrate this, the answer will just be the ln of the bottom, basically. But then there are cases where those laws do not apply, and all you may be required to do is to resolve the fraction into partial ones. So compound fractions are classified based on the nature of their denominator. So how the type of compound fraction you're dealing with is differentiated by the nature of the denominator. So we're going to look at this one after the other. We have four types looking at the denominators. And the very first one is this example where you have a compound fraction, where you have compound fractions with denominators involving non-repeated linear factors. Non-repeated linear factors. Now, a factor is linear if the highest power it has is 1, you know, or, x raised to power 1. Then it is not repeated if, for instance, of course, x plus 2 is a linear factor, for instance. So it is not repeated if this is not raised to any power beyond, if this is also power 1. But if it is power 2 upwards, then you say it's repeated, right? So that's the first example we are considering, compound fractions with denominators involving non-repeated linear factors. So for instance, we want to evaluate the integral of b plus 4 over b squared plus b within the interval from half to 1. Of course, you know, the result of this is going to be a single number because it is a definite integral. And of course, if you look at all the rules we followed, number one, you cannot divide this expression, just like the first example I cited just now. And then if you differentiate the bottom, the denominator, you get 2b plus 1, which is totally different from b plus 4. So the next thing is you can see that the denominator can be factorized, b squared plus b. You can factorize that. So in that case, we know we are dealing with a compound fraction that needs to be resolved. So we resolve b plus 4 all over b squared plus b into partial fractions. And how do we do that? B plus 4 over b squared plus b is the same thing as b plus 4 over b into b plus 1. So b is a linear factor. The first b is a linear factor. B plus 1 is also a linear factor. And you can see it's b plus 1 into b plus 1 raised to power 1. So because it's just b raised to power 1, right? Because it's just b raised to power 1, then it is linear. Then, and because, so b is already linear, right? But, if you add b squared, b itself is already linear. So if it is raised to power 2, then that makes it repeated. Then b plus 1 is linear. But then the fact that it has power 1 makes it non-repeated. So if you had power 2, power 3 upwards, it would be linear factor that is repeated. Okay, you'll understand this idea of repetition when we take other examples. But right now you have b squared plus b factorized in such a way that it is a product of linear factors. So one of the linear factors is b, the other linear factor is b plus 1. And once you have this, anytime you have linear factors like this expression here, this next expression is what determines whether you're going to get it right or wrong. So once you have confirmed that this is a linear factor and this is also a linear factor, then to break it down, all you just need to do is to put a constant over each of the linear factors, because a linear factor has more. So here you have b, say you have b raised power 1, right? So you should always put, okay, well, when we get to other examples, I think you will understand what I'm trying to say, because trying to explain that totally here may not make the full sense I wanted to make. But let's see. So linear factors, just put constants over them. So so you can have this expression to be similar to a constant a all over b plus a constant b all over b plus 1. So that's, here you have two linear factors, a product of two linear factors. So, and once you have this, then you can go ahead and all you're trying to do is to break this expression down into partial fractions, because right now it's a compound fraction. Okay. So, and once you get this done, the next thing is pretty easy. You can multiply through by the LCM. The LCM is b into b plus 1. So if you multiply this by b into b plus 1, this cancels out. So you have only b plus 4 left. And if you multiply a over b times b by b into b plus 1, b cancels out and you have a times b plus 1. And if you multiply b over b plus 1 times by b into b plus 1, b plus 1 cancels and you have b. So you have big B and small b. And that's why you have this, right? So here now you multiply through by the LCM and you end up getting this. Okay. And we can move on. Our aim at the end of the day is to break this expression down. And if you do that, if you use the cover-up method, okay, I think I'll have to explain the cover-up method because I think it's really essential. You have b plus 4 into a plus b, b plus 4 equals a into b plus 1 plus b. Okay, that's what you have there. So the cover-up method simply means that you're comparing coefficients. So for instance, let me change the color and do something here. Okay, so if you expand this, right, that is b plus 4. That is b plus 4 equals ab. Okay, no. For the cover-up method, I think it's even simpler than that. The cover-up method is really easy. For cover-up method, all you just do is try to set either this or this to 0 in tons, and then you get whatever is left. So if you say b equals 0 now, small b equals 0, that means that you have 0 plus 4, that's 4, equals b equals 0, that's 0 plus 1. So you have a there, plus b into, so this also becomes 0, b times 0, that's gone. So a is 4, settled. Okay, so now you have a as 4. The next thing to do is, if you want to set, so by setting b equals 0, we automatically cancel this part out. So once you've canceled that out, b is gone and you can find a. So how do you cancel a? To cancel a, just look at b plus 1 that is multiplying. It's just b plus 1 equals 0. That means b equals minus 1, right? So if you now say that, if you do this at b equals minus 1, it means you have minus 1 plus 4, that is 3. That's minus 1 plus 4, that's 3, equals minus 1 plus 1, 0 times a. A is gone. Then b times minus 1, that's minus big B. So that's why big B would be minus 3. And already what we had before was to break this down into a over small b minus, plus big B over b plus 1. Now a is 4, like we got here. So you have 4 over b. Then b is minus 3. So you have minus 3 over b plus 1. And that is why we have this expression right here. That's why we have that result. So that's the cover-up method. The cover-up method, you try to set values to, set the small b to values that will cancel one of the terms out so you can find the other. Okay. So with that, we get we get what we have now. So using the cover-up method from equation 27 was the last equation we saw before getting here. So when B is 0, for instance, you see that A is 4, just like I did. When B is -1, B is minus, small b is -1, big B is -3. And as such, B plus 4 over B squared plus B, this is what we broke it down to be. So our job was to look for A and B, and now we found A and B to be 4 and -3 respectively. So we can put them here and we get that. So with this now, you have this compound fraction resolved into two fractions, into partial fractions, 4 over B minus 3 over B plus 1. Okay, so now you can come back to say integral from 1 over 2 to 1 of B plus 4 over B squared plus B dB is equal to, so this same thing now is this 4 over B minus 3 over B plus 1 from half to 1 dB. Okay, so now you can break it apart. So 4 is constant, so you can take that 4 out here. 3 is constant, you can take that 3 out here. And then you have 1 over B dB left. That's 4. Normally it should be 4 over B dB. So because 4 is out, you have 1 over B dB minus 3, 1 over B plus 1 dB again. But then you see that if you differentiate B, you get 1. All right. If you differentiate B plus 1, you also get 1. Okay. So in that case, it means that it's easy now to just say for the lane of B. Now, it's important to say absolute value of B. Absolute value means whether it's minus or plus, we don't care. So, but because you can only leave, it only makes sense to find the log of a positive number, so to speak, in this sense. So you have the log of absolute value of B, here, because if you differentiate B, you get 1. Minus 3, log of the absolute value of B plus 1 also. But of course, don't forget that you have to take that from half to 1. So that's left. So you have 4 ln B. So you evaluate that at 1. So you have 1 minus, evaluate it at half also. You get that. Then the same thing applies there. You have 3 ln. So evaluate it at 1. You have 1. So the absolute value, right? 1 plus 1, you have it here. Minus half plus 1, you also have it right there. So we keep on, and then we have 1 minus half, that's half. 2 minus 3 over 2, that's also half. So finally we have 4 ln half minus 3 ln half. 4 minus 3 is 1, so this is basically ln half. And if you like, you can say that's ln 2 raised power minus 1, because 1 over 2 is the same thing as 2 raised power minus 1. That's ln 2 raised power minus 1. And then the minus goes to the back, and you have, from indices, the power can come down. So you have minus ln 2, and minus ln 2 is minus 0.6931. Because that is a definite integral, then you get this kind of situation. So that is when you have your compound fraction that can be resolved based on the denominator, right? Based on the denominator, you can factorize it into two linear factors that are non-repeated. Okay, let's look at other examples. So like I told you, there are 4 of them. So we've taken care of the first one. Now, how about if we have compound fractions, right, with denominators, compound fractions with denominators involving repeated linear factors. So we've seen linear factors. Now we want to talk about repeated linear factors. So here, just say this. We want to evaluate integral dc over c squared minus 1 all raised to power 2. So, we can resolve this. You can see this already. C squared minus 1 is difference of 2 squared. C squared minus 1 raised to power 2. So this alone, you can express that as c minus 1 into c plus 1. Then everything is now raised to power 2. So it means you have c minus 1 squared into c plus 1 squared. So you see, this is linear, but it is repeated because it has power 2. C plus 1 is linear, but it is repeated because it also has power 2. So, and that's exactly what we are doing in this case. Okay, so to resolve this now, that it's just what I've done. So you have 1 over c squared minus 1 raised to power 2 equals, of course, first of all, you check, can you differentiate this, integrate this directly? It doesn't look like that. You can't divide. If you differentiate the bottom, you don't get anything at the top. So it doesn't make sense. So you have to keep going. Okay. So c squared minus 1 is c minus 1, c plus 1, and it's all squared. Then you now have this to be 1 over c minus 1 squared, c plus 1 squared. So linear, power 2 means they are both repeated. So that's why we have compound fractions with denominators involving repeated linear factors, okay? So with this now, how do you handle repeated linear factors? So again, you come and since you have c minus 1 squared, c plus 1 squared. So for repeated linear factors, the idea of repetition really comes up here. So if you take the first a, since it is linear, right, you still use a. So you take a over c minus 1, that's for the power 1. Then you take b over c minus 1 raised to power 2. Then if you had 3, like if you had c minus 1 raised to power 3, then you still go ahead to say c over c minus 1 raised to power 3. But it is just power 2, so we stop there. Then you have the same for c plus 1 squared. So you take the next letter c, capital C over C plus 1 plus D over C plus 1 squared. So if this one goes up to 7, so you have to keep going. C over C plus 1, D over C plus 1 squared, E over C plus 1 cube, F over C plus 1 raised to power 4. You keep going until you get to 7. That's what it means for the linear factor to be repeated, right? But here we just have 2, so we just go A for the C minus 1, B for C minus 1 squared, C for C plus 1, and D for C plus 1 squared. And now that we have this, once you're able to write this correctly, then you are on track. But once you get it wrong here, then there's little hope of success. Okay. So here, since we have this sorted out, of course, usually this would be the LCM, with which you can multiply through. So if you multiply through by this, you get automatically 1 here. If you multiply by c minus 1, c minus 1 cancels one of this, and that's why you have a into c minus 1 plus c plus 1 squared. C minus 1 squared cancels c minus 1 squared. So that's why you have b into c plus 1 squared. So talking about c plus 1, right? For c plus 1 cancels one of this. That's why you have b into, that's why you have c rather. You have c into c minus 1 squared, c plus 1, because one of c plus 1 is gone. And then if you have c plus 1 squared, all of this is gone. So you have d into c minus 1 squared left. So we've tidied it up that way. And the next thing, we can go ahead to do cover up, like we did before. So if you look at the cover up, right, see what is going to happen. You want to set things to 0 as much as possible. One thing we can do here is that if it makes c to be 1, right? If you make c to be 1, automatically this will go. Anywhere there's c minus 1 will go. This will go, and this will also go. So it means we have 1 equals that. When we set small c to be 1, everywhere there's c minus 1 will go. So you have this one on the left-hand side, and then c is 1, right? 1 plus 1 is 2, raised to power 2, 4. So that's 4b. And that implies that b is equal to 1 over 4. So we get b that easily. You see, so when c is 1, you get b equals 1 over 4. That's straightforward. Then we can also do the next one that easily, but it gets a bit complicated afterwards. Okay, what if so we have got b to be 1 over 4, right? What if we set, of course, there's also c plus 1. So if you want to get rid of anything c plus 1, you have to say c equals 1. So if c equals minus 1. So at c equals minus 1, everywhere you have c plus 1 will also go. This will go. Everywhere you have c plus 1 goes. So you again have 1 on the left-hand side. And on the right-hand side, since c is minus 1, so you have minus 1, that's minus 2, raised to power 2. That's also 4d. So that implies that big D is also 1 over 4. And that's why you have this D here. At c equals minus 1, D is 1 over 4. So, and that's all we can have. So, but then, since direct cover-up will not work, we can now do random cover-up, so which can lead to simultaneous equations. For instance, you start with very small numbers. You use 1 and minus 1. So you can consider something like 0. So if you say at c equals 0, so here you can use any number you like, but the smaller the better. Okay. After you have used the specific ones that will cancel things out, then you can begin to now use all kinds of any number that comes to you, no matter how big or small. But the smaller the better for easy calculations. So at c equals 0, right? 1 equals c equals 0 here. So it means you have a into minus 1 into 1 all squared plus b into 1 squared again plus c into minus 1 squared into 1 plus d into minus 1 squared. So that means you have 1 equals, what's this? So this is minus a plus b, then here plus c now, and here plus d. Interestingly, you already know, what do we know already? We know we know b and d. B and D, we know them to be 1/4 each. So this is 1 over 4, and this is 1 over 4. That's like 1 over 4 plus 1 over 4 is half. So you can cancel this out, right? And you have half. So if you take half to the other side, so it's like 1 minus half, you know. so this one now minus this half that will come from here, that's actually half equals minus a plus c. If you multiply through by 2, because it's better to avoid working with fractions if you can. So multiply through by 2, you have 1 equals minus 2a plus 2c. So minus 2a plus 2c. So you can see, of course, to make things easy, so you can multiply through by minus. So you get minus 1 equals 2a minus 2c. And that's why you have this expression right here. 2a minus 2c equals minus 1. So you have an equation. So you now, we have got b and d. We need a and c. And since we can't get a and c directly, we can use random values to get equations that will lead us to, to get a and c. So I've used c equals 0. What if we use c equals 2? That's another thing we can do. Again, let's go. If we use c equals 2, this is what is called the cover-up method, right? You want to be skillful. There's another way you can expand and compare coefficients, and that's a lot of process. But cover-up works anytime, any day. You just start with canceling the things you can cancel immediately, like by setting c minus 1 equals 0, you get c equals 1. So anywhere once you put 1, anywhere there's c minus 1, all that will go. Then because of c plus 1 equals 0. So if you set c to be, c plus 1 equals 0, so that means if you say c equals minus 1, everywhere there's c plus 1 also cancels out. But then if that is all done, then you can now assign random values, as small as possible for easy work. So we've done for 0, and we've got an equation. All right. So we've got the first equation. Let's do at c equals 2. You could as well just say c equals 3 or anything, but the smaller the better. So at c equals 2 now, so we have 1 equals c equals 2. So for this, we have a into 2 minus 1 is 1. 2 plus 1 is 3. So we have 3 squared plus b into 3 squared again. 3 squared again, then plus c into 2 minus 1 is 1 into 3, 2 plus 1, then plus d, which is 2 minus 1, which is also 1 squared. So here we have 1 equals 9a plus 9b plus 3c plus d. And of course, we already know that b and d are 1 over 4 each. So this is okay. This is 1 over 4, and this is also 1 over 4. So it's more like you have 9 times 1 over 4. That's 9 over 4 here plus 1 over 4 here. That's like 10 over 4. So 1 minus 10 over 4, if you carry this 10 over 4 here, so you have 4 over 4 minus 10 over 4. That's like minus 6 over 4. This one minus the 10 over 4 that will come from here. That's like minus 6 over 4. Then equals 9a plus 3c. 9a plus 3c. And you see 3 can go here twice. 3 goes here, you have 3a. 3 goes here, you have c. So if you multiply through by 4, you have minus 2 equals 12a plus 4c. 12a plus 4c. 2 can still go, right? So if you divide through by 2, you have minus 1 equals 6a plus 2c. 6a plus 2c. And that's exactly what you have here. So you have 6a plus 2c equals minus 1 again. So you have these two equations. So you can solve these two equations for for a and c. So interestingly, this is pretty easy. You have 6a minus 2c equals minus 1. And you have 6a plus 2c equals minus 1. So you can easily add, because if you add this, if you add this, minus c plus 2c is 0. So here you have 12a equals, if you add minus 1 and minus 1, you get minus 2. So a is equal to minus 2 over 12. That's minus 1 over 6. And that is why, is that minus? Oh, sorry, this is 2a, sorry. So this is 8a, sorry. 2a plus, okay, maybe I shouldn't have gone that far. I could just do it here, since I can easily erase. So add up this. So 2a plus 6a is 8a, minus 2c plus 2c is 0, and this is minus 2. So divide through by 8. So you simply have a to be minus 1 over 4. That's why a is minus 1 over 4 here. And that's a settled. How about and since a is settled, right? A is 1 over 4. You can simply use any of the equations to get c. So you have 2 into minus 1 over 4 minus 2c equals minus 1. So this is minus 1 over 2 minus 2 over 1 C equals minus 1. So this is like minus 1 over 2 plus 1 over 1. Bring this here, and then this is equal to minus 2C, right? So this is like 1 over 2, minus half plus 1, this minus 1 over 2 minus 2C. So this is minus 4C equals 1. So C again is minus 1 over 4. Is it minus 1 over 4? Okay, sorry. Okay, minus 2C goes there to becomes positive. So you see C is 1 over 4, like that. So with that, we have all the numbers sorted, because the purpose actually is to get every term here. Once you break it down properly this way, so the next game is to get A, B, C, and D. And we have got A, B, C, and D right now. So with that, we can come back and say, so 1 over C minus 1 squared, C plus 1 squared equals A over C minus 1. So A now, we know is 1 over minus 1 over 4. So that's why you have minus 1 over 4 here for A. And then for B is 1 over 4. So you have 1 over 4. C, what is C now? C is 1 over 4 again. And of course, D is also 1 over 4. So you have this 1 over 4. So you have been able to break down that expression, though it looks really laborious, but I mean, it's not beyond you. So you need to practice this more, over and over again, if this is your first time of dealing with this. So now we have been able to break this simple looking thing down into this long thing. So the next thing is to go integrate, okay? So to integrate this now, see what we have. So we have this integral of all these DCs now, integral of the breakdown, DC, okay? So, and we can do each one separately. So this is minus 1 over 4. We can bring that out, and we have 1 over C minus 1 DC. Then 1 over 4 again. This comes out. We have 1 over 4 right here. So 1 over C minus 1 squared. And then again, we have, same here. We have 1 over 4 integral 1 over C plus 1 DC. And this again. And, if you do all this, you get this. So if you differentiate C, you get 1. So automatically, that's minus 1 over 4 in C minus 1. And for this now, you can use substitution. So you can use substitution method. Let's see, you have 1 over 4 integral 1 over C minus 1 squared dc. So if you say, let u be equal to C minus 1, okay? So it means that du dc is equal to 1. That simply means that du equals dc. And then what do we have to change again? I think that's all. So we have integral 1 over u, which is u raised power minus 1. And dc now is simply du. And if you integrate this, you get, if you integrate this, oh, it's power 2, right? This is power 2, sorry. I was wondering. So this is now u raised power minus 2. So if you integrate that, that's u raised power minus 1 divided by minus 1. So that is minus u raised power minus 1. And that is minus 1 over u raised power minus 1. You remember, minus 1 is C minus 1. So you have C minus 1. We'll come back there. So that's minus this. So it means that this whole expression, if you integrate it, actually, so of course, don't forget the 1 over 4 outside. So 1 over 4 times minus 1 over C minus 1. And that is why so if you integrate the whole of this, you get minus 1 over 4 C minus 1. This minus is what we have outside here. The 1 over 4 is there, and then this is C minus 1. So that works for that. And then, of course, coming here, it's pretty easy. Differentiate C plus 1, you get 1. So it means you have 1 over 4 in C plus 1. Of course, don't forget the absolute value to guarantee that it's positive. And then for this one too, the treatment is just like what we've done here. So the only thing is that instead of u equals C minus 1, you have u equals C plus 1. And at the end of the day, you still get exactly the same kind of expression, except that this is now C plus 1 plus K. And then that is it. I mean, it looks pretty clumsy, but try to follow patiently, and then you'll be fine. So don't forget to integrate this, right? Here, you just differentiate C minus 1, you get 1. So it means the answer is ln of c minus 1. Of course, don't forget to multiply 1 over 4. And for this, use substitution, algebraic substitution. So you can say let p or u or anything be c minus 1. And then if you do that, you end up getting minus 1 over 4 c minus 1. Then again here, it's the ln thing. Differentiate c plus 1, you get 1. So ln of c plus 1. And again, algebraic substitution here. And that's how you get the answer for that. Okay. So that's the second situation when you have repeated linear factors. So it's also possible to have compound fractions with denominators involving irreducible non-linear factors. Irreducible non-linear factors. So when something is linear, if the highest power it has is 1, right? You know, if you have ax plus b, that is linear. But if you have ax squared plus bx plus c equals 0, this is quadratic because the power is 2. So when something is nonlinear, it means that it is not, it has power 2 upwards, or it has it is some kind of expression that you cannot, that does not give you a straight line, like maybe some transcendental function too. Okay, so not compound fractions with right? With denominators involving irreducible nonlinear factors. Okay, so the denominator has factors that are non-linear and that cannot be reduced to linear. You know, it's possible if you have b squared minus 1, it is non-linear, right? But it is reducible to b minus 1 into b plus 1. So this is reducible non-linear. Okay, so but then if you have b squared plus 1, that's nonlinear, and it is irreducible rather. You cannot express it as a product of linear factors. So that is what it means for something to be irreducible in that sense. Okay, so that's what we are dealing with now. So a very good example is this: to evaluate integral of f squared over f raised to the power 4 minus 1 df. So first we need to resolve this. Now you have already seen that if you differentiate f raised to the power 4 minus 1, you get 3f cubed, and it has nothing to do with f squared here. So and then you cannot divide through like we've always done. So the next thing you want to do is to resolve into partial fractions. So, and then you see this is f squared over f raised to the power 4 minus 1. So f raised to the power 4 minus 1, f raised to the power 4 minus 1 is the same thing as f raised to the power 4 minus 1 raised to the power 4. And that is like f squared squared minus 1 squared squared. That's like difference of two squares, where you can now have it to be f squared minus 1 into f squared plus 1. That's the idea of difference of two squares. Again, you can go further. So you have f squared over f squared minus 1, f squared plus 1. Now, next thing is this. You see that f squared minus 1 here can actually still be represented. So the f squared minus 1 can still be broken down further into f minus 1, f plus 1. So this is linear now, but it is reducible. So we have been able to reduce this to two lines. So this is linear, non-repeated. But then this cannot be reduced. So this is quadratic, that is non-linear, and it cannot be broken down further. Now, see how we treat them. We already know how to treat linear factors. Just put a constant over them. But for non-linear factors, right? So whatever the power is, whatever you're going to put on top of it we start from if a power of the variable that is 1 less than the power. Now, what that means is this. So here now, you now have f squared over f minus 1 into f plus 1 into f squared plus 1, like you have here. And that is, so this breakdown like is extremely important, like I've been saying. So you need to know how to approach it. So this is linear. So you can just put a over f minus 1. This is also linear. You have b over f plus 1. But this is quadratic, power 2. So whatever you have at the top of it should start from should have power 1. So in that case, instead of just putting c over f squared plus 1, that won't work. But because this is quadratic, you have to now say cf plus d. So if it was like x squared plus 1, so this would be cx plus d. So if it was power 3, right, you have to have cf squared plus df plus e. If it was power 4, you have cf cubed plus df squared plus ef plus g, something like that, or plus f. So this part now is the irreducible nonlinear factor that we have here. You know, of course, linear, we have seen that before. So once you're able to do this correctly, then you are on course to get things right. So again, once you do that, the next thing is to multiply through by the LCM, which is all this. And that's why you have f squared here, and that is equal to, So multiply this term also by all that. So f1 minus 1 cancels f minus 1. That's why you have a into f plus 1 into f squared plus 1. And then you go again for b. So for b, f plus 1 cancels f plus 1. So that's why you have b into f minus 1 into f squared plus 1. Then lastly, you have cf plus d all over f squared plus 1. So f squared plus 1 cancels f squared plus 1. So you have cf plus d into f minus 1, f plus 1, like that. And once that is done, the next thing is to do the cover-up thing so you can get those factors. Of course, the first cover-up you can do, okay, maybe I should do it somewhere in the middle here so where we can see everything. So now the first cover up we can do is this. We can already see, I see f plus 1 and f minus 1 featuring prominently. So I also see f. Oh, okay, no, this won't work because there'll still be d. Okay, good. So I see f minus 1 and f plus 1. So the easiest thing is just say at f equals 1. Once you set f equals 1, everywhere there's minus 1 will just go. So this will automatically go, and this will automatically go. So, and since f is 1, so you can just evaluate this. So if f is 1, f squared is 1 on the left-hand side. On the right-hand side, you have a into f plus 1, that's 1 plus 1, which is 2. Then f squared, that's 1 squared plus 1, another 2. So you have 4a equals 1. So a again is 1 over 4. And that is what we have. If at f equals 1, a is 1 over 4. Okay? So the next thing we can also do is so a is already set to be 1 over 4. What if the other thing we see again is f, we also see f plus 1 here. So you can now set at f equals minus 1. So once you say f is minus 1, so minus 1 plus 1 is 0. It automatically cancel out anywhere there is f plus 1. This will also go, right? So then it means that on the left-hand side, minus 1 squared is still 1. And on the right, you have b into minus 1 minus 1, that's minus 2. Then minus 1 squared is 1 plus 1, that's also 2. So you have 1 equals minus 4b. Oh, did I get that right? I think so. Yep. Okay. So I think that's okay. So B is now minus 1 over 4. Mind you, it's not, it's not that in every situation you must get 1 over 4 minus 1 over 4. It's just coincidental that all these things are giving us that 1 over 4 thing. It can be actually anything. Thankfully, we are going to say D is not that. So now that you have done 1 and minus 1, so we have got A and B. So we still need C and D. So how do we take care of those? So again, you can just use small numbers like 0 and co. So now let's say now there's nothing that will cancel directly. So we can now take random values of f as small as possible. So at f equals 0, right? If f is 0, so the left-hand side will be 0, right? 0 squared is 0. So this will be a into 0 plus 1, that's 1. Then 0 squared is also 0, then plus 1, that's 1. Then plus b into minus 1 into 1, because this is 0 squared plus 1. Then here we have plus cf plus d into f minus 1, f plus 1, that's minus 1 into 1. So we tidy that up, we get 0 equals a minus b, cf plus d into minus 1, right? So that'll be minus cf minus d, minus cf minus d. But we already know a and b. A and b are 1 over 4 and minus 1 over 4 respectively. So this is, if I'll change colors here, so you have 1 over 4, 1 over 4, minus b, that's plus another 1 over 4, minus cf minus d. So this is like, if you bring cf minus d to the other side, so you have cf, oh, f is 0, right? Oh, interestingly, this also cancels out. Great, that's so sweet to know. So now you just have, straight up, you have your d. So you have 0 equals half minus d. So that means that d is equal to 1 over 2 easily. So d is 1 over 2 because cf is also gone. So you have d to be 1 over 2 like you have there. So again, I'm using 2. You can use anything, don't forget, you can use anything. But we're using, since you have used minus 1 and 1, we are using very small numbers close to 1 and minus 1. So now I want to say at f equals 2, at f equals 2, f squared on the left hand side, that'll be 2 squared, which is 4. On the right hand side, that'll be a into 2 plus 1 is 3. 2 squared is 4 plus 1, 5. Then plus b, b, f minus 2 minus 1 is 1. 2 squared plus 1, that's 5 again. Then cf, that is 2c plus d. Then 2 minus 1 is 1. 2 plus 1 is 3. So we have 4 again equals 15a plus 5b. Then, so we have, this is 3, right? So plus 6c plus spirit. So this is 3 times 2c, that's 6c, plus 3 times d, that is 3d, right? So, and we already know that uh, A and B, we have values for them already. So A and B would be, A is 1 over 4, B is minus 1 over 4. So, this is 15A, right? This is 5B. So we have 15 over 4 minus 5 over 4. That's like 10 over 4, right? If you take that to the other side, so you have 4 over 4 minus 10 over 4. 4 over 4 minus 10 over 4. That's 16 over 4 minus 10 over 4. That is 5. That's 6 over 4, which is 3 over 2. So you have 3 over 2 equals 6c plus 3d. So I think we already know d also to be half, right? I should have done that. So 3 over 2 equals, this is half. So 3 over 2 minus 3 over 2, that is 6c. That is c equals 0, I think, because this is 0 and 6c is 0. So simply c is 0, but from all that. Okay, so the next thing is that you have, so it means you now have f squared over f raised to power 4 minus 1 broken down into, so don't forget where you're coming from, a over f minus 1, that's 1 over, a is 1 over 4, so you have 1 over 4 f minus 1, then b plus b over f plus 1, and b is minus 1 over 4, that's why you have this minus 1 over 4, and then c, so you have cf plus d over f squared plus 1, so now c is 0, so you have 0 times f, that's 0. So you have only d left. D is 1 over 2. So you have 1 over 2 into f squared plus 1, like this. So with that sorted, then you can move on. So this is the expression you have to integrate now. So the integration goes as follows then. So I mean, like we've done before, you can do that. So you have 1 over 4 is out here. So you have 1 over f minus 1. Then you have minus 1 over 4 out here again, 1 over f plus 1. And you have 1 over 2 out here, all over f squared plus 1. So in this case, so of course, if you differentiate f minus 1, you get 1. Differentiate f plus 1, you get 1. So automatically, that is 1 over 4 in f minus 1, minus 1 over 4 in f plus 1. And here, you can, if you differentiate f squared plus 1, you don't get 1. So that's it. That's an issue. So you have to do trigonometric substitution. This looks like those cases of x squared plus 1, or a squared plus x squared, or x squared plus a squared, where you now say f is equal to say a tan theta. A here is 1, so f is equal to tan theta. And once you, so it's more like you have integral of 1 over f squared plus 1 df, and now f is tan theta, so the theta is equal to sec squared theta. So in that case, it means that you have, okay, let me change this. So it means this is now integral of 1 over f squared now. So since f is tan theta, so you have tan squared theta plus 1, all right, times df. df now will be sec squared theta d theta. So this is sec squared theta d theta. So that all this can go, all right, and then you just have um so you have this to be equal to integral of tan square theta plus 1 is sec squared theta times sec squared theta d theta, right? So this cancels out. So you just have integral of d theta. And what is d theta? So the integral of d theta is simply theta. Now, don't forget, you said f is equal to tan theta, okay? So it means that theta alone will be, so you have to take arctan of both sides. So theta is equal to arctan of f, arctan of f. And that is why if you integrate this expression, you get arctan of f, but there's half outside. So you have 1 over 2 arctan of f plus constant c. And that's how it goes. So you can really write that down, like try to integrate this alone and you'll understand better. So that theta is arctan of f. And that's how that goes. So the next thing is, so that is the third kind of denominator you can have. So let's go to the next one. This is really a lengthy one because of the intricacies of what the denominators can look like. Okay, so we can have another type of denominators where we have improper compound fractions. You remember the idea of improper fractions. A proper fraction is something like 2 over 3. You know, 2 is smaller. The numerator is less than the denominator. But what if you have 3 over 2? This is an improper fraction because the numerator, so here, numerator is less than denominator. But here, numerator is greater than numerator. Numerator is greater than denominator. So this is improper. Whereas this is proper, right? So the same kind of thing applies to compound fractions. So how do you know that a compound fraction is proper? A compound fraction is only proper if the power of the numerator is less than the power of the denominator. Okay, so, and by power I mean the highest power of the variable we are under consideration. So, but then if the power of the numerator is greater than or equal to the power of the denominator, then you say that is improper. And once it is improper, there's an approach to handle that, which is why we're here. So for instance, look at this now. The highest power of G is in focus because you are integrating with respect to G. So since G is in focus, for the numerator, the highest power of G is 3. And the highest power of the denominator is 2. So automatically this is improper because the power of the numerator is greater than the power of the denominator. Even if the power, the highest power here is 2 and the highest power here is 2, it is still improper. The only time it is proper is all the cases you have seen before where the power at the top is smaller than the power below, you know. So once the power at the top and the power below are the same, or the power at the top is greater than the power below, then you have an improper compound fraction. So once you have identified that power dynamic, then you can easily decide. So here, clearly, this expression is an improper compound fraction. So, and the way to deal with that is what we are going to see now. So here we have to resolve this into partial fractions. But first, the fraction is improper, so we have to evaluate to identify the whole and the fraction parts. So how do you evaluate to know the whole and fraction parts? That you have to do long division. So this is the idea of long division. So you have this expression and you have 3g cubed minus g squared minus 13g minus 13, and then you're dividing by g squared minus g minus 6. Okay, so you now take g squared in 3g cubed, you have 3g. So 3g times 3g cubed, 3g squared, that's 3g cubed. 3g times g, that's minus 3g squared. Now you try to subtract. So 3g cubed cancels 3g cubed. So minus g squared minus 3g squared, that is 2g squared. All right. Then you can now bring down the minus 13g. So again, g squared in 2g squared, that is plus 2. So 2 times g squared, that is 2g squared. 2 times minus g. Okay, I think I didn't complete this. So here, 3g minus 6. 3g minus 6 would be minus 18g, right? Minus 18g. So if you subtract again, this is like plus 6g down here, plus 6g. Okay, so now if you have g squared in 2g squared, that's 2g, that's 2 times g squared, that's 2g squared. 2 times minus g, that is Okay, I have to 2g squared, right? Okay, of course, this is still okay. This is okay. Plus that is plus 18g. Plus 18g. Okay, I guess I have to do that again. Okay, here before you have 18g here. So this is actually plus 6g for sure. Then now that g squared has gone into 2g squared, you have 2g. So 2 times g, you have 2 times g squared is 2g squared. 2 times minus g is minus 2g. Then 2 times minus 6 is minus, of course, you have to bring down this minus 13, sorry. So 2 times minus 6 is minus 12. So if you subtract now, this cancels this straight up. Then 6g minus minus this, you have, is that 8g? Okay, I guess I have to do this again. Sorry. Let me do this again for clarity. So now the long division, you have 3g cubed minus g squared minus 13g minus 13, and then you're dividing by g squared minus g minus 6. So g squared in 3g squared, that is simply 3g. 3g times g squared, that's 3g squared. 3g times minus g, so you have minus 3g squared. Sorry, this is 3g cubed. The first one is 3g cubed. Then 3g times minus g, that's minus 3g squared. 3g times minus 6, that is minus 18g. Okay? So you subtract, and this cancels this. Minus g squared minus minus 3g squared, that's plus 2g squared. That's 2g squared. And then minus 13g minus minus 18g, that's plus 6g. Then you bring down the minus 13, okay? Bring down the minus 13. So g squared in 2g squared, that is actually 2. 2 goes in 2g squared twice. So 2 times 2g squared, that's 2g squared. 2 times minus g, that's minus 2g, okay? And then you have, okay, minus 13. Okay, 18 minus 13 is 5, actually. So this is 5, sorry. This is 5. Yep, 5. Yes, 5. So then 2 times minus g is minus 2g. 2 times minus 6 is minus 12. Yeah. So you now subtract. So 2g squared cancels 2g squared. Then you have 5g plus 2g. That is 7g. Then minus 13 minus minus 12, that's minus 13 plus 12, that's minus 1. So you see, this is the, so at the end of the day, g squared cannot go in 7g, so that's where you stop. So this is like the whole number part, and this is like the fraction part. Just like in the case of every improper fraction, 3 over 2, that's one whole number, 1 over 2. So this one now is like what you got at the top here. This one on top here is like this 7g minus 1. And that is why, with all that done, we can now express that improper compound fraction. We can express this improper compound fraction as 3g plus 2 plus 7g minus 1 all over what we divided with, that's g squared minus g minus 6. So now this is whole number. This is now a proper compound fraction again, because I can already see that of course we can't divide. We have to really still resolve this further. So that's what we are doing next. Let's go to take care of that. We have taken care of the fraction part. I mean, the whole number part, which is already 3g plus 2. So for this now, so see what we have. So we now have to resolve 7g minus 1 over g squared minus g minus 6 into partial fractions. So the first thing is you have 7g minus 1 over g squared minus g minus 6, and that is equal to 7g minus 1 over g plus 2, g minus 3. Right? Okay, well, of course, to factorize this now, this is g squared minus g minus 6. So you need two numbers. When you multiply, you get this minus 6. But when you add, you get this minus 1 in between. And these two numbers have to be factors of minus 6. And then that's simply 2 and 3. So, but which one will give you this? So it has to be minus 3 and plus 2. Okay? So it means that you have minus 3 plus 2. So that means that you have g squared, minus 3g plus 2g minus 6. So take common value. So you have g into g minus 3 plus 2 into g minus 3. So you have g plus 2 into g minus 3. And that is why you have that expression, right? So here you have 7g minus 1 over g squared minus g minus 6 to be the same thing as 7g minus 1 over g plus 2, g minus 3. So these are linear factors now, and they are not repeated. So you just say a over g plus 2, b over g minus 3. And it's easy peasy. You can do cover up easily. Of course, if you put g to be minus 2, this part will go out. So you have minus 2 minus 3. That's minus 5a equals, since g is minus 2, so you have 7 times minus 2, that's minus 14. Minus 14 minus 1, that's minus 15. So A is simply 3 that way, easily. Then the other cover up you can do is to make G to be 3. Once G is 3, if you put G to be 3 here, this part goes out. So you have 3 plus 2, 5. 5, so you have 5b equals 7 times 3, 21 minus 1, that's 20. So now b is equal to 4, like you have right here. So in that case, we can say 7g minus 1 over g squared minus g minus 6 is 3, because a is now 3. So you have 3 over g plus 2 plus 4 over g minus 3. So finally, you can bring up together the whole expression. So you have 3g cubed minus g squared minus 13g minus 13 over g squared minus g minus 6. So you have 3g plus 2, then 3 over g plus 2 plus 4 over g minus 3. So now you have these things well simplified, and then you can integrate these ones now instead of integrating this complicated stuff. So let's see how we integrate all that. So the integration part, you see, is the easiest part, but that resolving it into partial fractions is a very challenging one. So you have this whole expression now to be 3g plus 2, 3 over g plus 2, 4 over g minus 3. So that now you have 3g, so the 3 can come out. So you have g dg plus 2 dg, this is constant. Then you have 3 out, 1 over g plus 2 dg plus 4, 1 over g minus 3 dg, like that. So easily you can go on. This is g dg, so increase the power. This is g raised power 1, g raised power 2 divided by 2 plus 2g, because this is dg. So integral of dg is g, just like I've told you times 2. You have 2g, then integrate g plus, differentiate g plus 1, you get 1 straight. So that's 3 ln g plus 2. Same, differentiate g minus 3, you get 1. So that means you have ln of g minus 3 plus c. So all this now brought together is the answer to that troublesome expression. So you have 3 over 2g squared plus 2g plus 3 ln g plus 2 plus 4 ln g minus 3 plus c. And with that, we come to the end of this lengthy part of integration. That's integration of compound fractions. So when you have compound fractions, you resolve into partial fractions for easy integration. So if you have not subscribed to this channel, please do that and press on the click on the notification button so you can always get notified when I have a new video. So after this, I'm going to do the last video on integration. That'll be showing you some general formulas and several practice questions you can try your hands on. Thank you for listening. See you in the next one.